Welcome to Knowledge Hub by Sri Chaitanya, and I also welcome you to these live sessions where we have been discussing about the first chapter of 11th chemistry, some basic principles of chemistry. Now, let me welcome you to the fifth session where I am going to throw some light on laws of chemical combination. Right? Why are these laws important? Well, obviously, it is according to these laws that various chemicals in the environment, in the lab, in our body or outside our body combine to give you useful molecules. So now let's have a look at the first law. Let us also look at the laws which we are going to study in these. The first law is law of conservation of mass. The second one is the law of definite proportions, the law of multiple proportions, the law of reciprocal proportions, the law of combining volumes, and finally Avogadro's law. So these 6 laws are the basis on which chemicals combine and form other chemicals, molecules or compounds. So let us have a look at the first law, law of conservation of mass. I am really sure that you have come across this law. This law says that mass can neither be created nor destroyed during a chemical change, right? If you do some chemical reaction, mass on this side will be equal to mass on the other side. See, so it simply means that the total masses of the reactants before the reaction. What is this total masses of reactants before the reaction? This is nothing but your left hand side, right? And the total masses of the products after the reaction is what? It is your right hand side. So simply add up the masses of the reactants given on the left hand side and also on the right hand side. Both of them should be equal. That is what I mean by law of conservation of mass. So have a look at this reaction where you have carbon solid forming oxygen gas and CO2. So we know that whenever a reaction like this is written, suppose this is the reaction, I am writing it down again. What does this equation signify? I have told you earlier also. If this equation is balanced, it means that 1 mole of carbon reacts with 1 mole of dioxygen, yes, dioxygen, to give you 1 mole of carbon dioxide, correct? And what is the molar mass or mass of 1 mole of carbon? It is 12 grams. Oxygen, and I mean O2, is 32 grams. And if you add up and get the molar mass of carbon dioxide, which is 12, right, this is 12, this is again 32, you add them up, you will get 44 grams. Simply you can see clearly here that if you add them up, you will again get 44, which is equals to 44 grams on the other side. Simply this mass is, this law is this. Another example, you have nitrogen, you have hydrogen and you have ammonia, right? This nitrogen, hydrogen and ammonia are there. So nitrogen's molar mass, one nitrogen atom's molar mass is 14, you have 2, so this is 28 grams. Hydrogen's dihydrogen has 2 grams as mass, there are 3 moles of it, multiplied by 3 and here you multiply it by 17, you will find that both the masses come out to be equal, right? Yes, I know you must be thinking that this is such a basic thing, right? Why do we have to learn it in the form of a law? Well, understand this, in ancient times, we did not have any laws of chemical combinations, right? When science itself was progressing and chemistry was progressing, it was proposed by Antoine Lavoisier, this law, right? So, it is important. Now, one place where this law actually does not work, is not applicable, that is in nuclear reactions. Remember that. In nuclear reactions, sometimes mass is converted into energy and in those reactions the conservation of mass is not followed, right? It may happen that on this side you have 14 grams and on this side you have 10 grams, right? So 14 minus 10 comes out to be 4 grams, right? So this 4 grams of mass, there is a possibility, has converted into energy according to this equation. Yes, this famous equation E equals mc square. The famous Einstein's equation, where this is the energy which is produced when this mass is converted into energy, and of course c is velocity of light. Right. Now, after law of conservation of mass, a question on that. Well, let me tell you that this is not a straightforward question. Right? So you have 6.85 grams of strontium hydroxide, right? And on heating it gives 3.13 grams of anhydrous strontium hydroxide. You have to find the value of X. What I want all of you is to pause this screen for a little bit, try and read the question and try it yourself. Done. So let me give you a hint also here that, see, molar mass of strontium is 121 grams per mole. Right. So let us first write down the equation. You do understand, right? What is this? What is this? This is water of crystallization, right? So when you heat such a salt, when you heat it, what will happen? Yeah, the triangle means heat. When you heat it, this water of crystallization separates out. This is a normal phenomena, happens everywhere. So 6.85 grams. So this is your 6.85 grams of this compound. On heating gives you 3.13 grams of anhydrous strontium hydroxide, right? And there is some grams of this. So according to mass, law of conservation of mass, can you tell me how much this will be there? Simply we know that will be equals to 3.13 grams plus weight of water, correct? Plus weight of water, right? Right. So if you just minus them, how much you are bound to get? 3.72 grams is the weight of H2, right? So that is how you calculate the weight of H2O here. But the question does not end here. This is a combination question of mole concept and law of conservation of mass. So here your law of mass conservation comes into picture. Yes. See, most of the times you will not get direct questions on this. It will be only when you have a combination question in which one of the steps will involve using this law, like here. So you have the mass of what? We have the mass of water that is produced. This comes out to be 3.72 grams, right? Now, how will you find the formula of this? How will you do that? Well, think about it a little bit. See, I told you whenever you have such questions, the one thing that you should do is you calculate the moles, right? You calculate the moles, right? Okay. So let us move forward in calculating the moles. Right. Sorry, it's not the molar mass of strontium here. 121 is the molar mass of strontium hydroxide. Okay, I think this will correct this out. It is this molar mass. Now we have to find the value of X, right? Now think about it. If you have to calculate the moles of this will be 121 plus 18x moles, right? Is this correct? Right. So these many moles gives how many moles of strontium hydroxide? Okay, let it be how many moles of water? 3.72 divided by 18 moles of H2. Right? These many moles of H2O you will get from these many moles of this. But for finding formula, we need what? We need the moles of H2O in what? What do we need? We need moles of H2O in 1 mole of the compound. Let me just write the full formula of the compound. Okay. Moles of H2O in 1 mole of strontium hydroxide hydrate. Now, how will you go about solving this? Well, let me make it simpler for you. Let me just erase the upper part and see, purely based on the unitary method, I am going to solve this now. See, so 6.85 by 121 plus 18x gives you these many moles of water, right? So can you tell me 1 mole of strontium hydroxide hydrate will give you how many moles of water? So if I talk about 1 mole of it gives how many moles? Think about it. So you have to find, see what basic thing I follow in unitary method is the thing which you have to find, which is moles of water that you have to find, you keep it in the numerator. So 3.72 by 18, you keep it in the numerator, and this part which you do not have to find, keep it in the denominator, means it has to be reciprocal. Right? So these many moles you will get of water. Right? I hope you have understood this. These many moles of water you will get. Simply from these many moles of compound you will get this many moles of water. Now I have to find moles of water in 1 mole of, from 1 mole of compound. Right? So you have to find moles of water. So what you have to find from the relation, put that in the numerator. What you do not have to find, put that in the denominator like this. and then finally multiply it by 1. See, I have not multiplied it by 1 here. Means multiply it by the quantity from which it needs to be calculated. Like 1 mole you have to calculate, so just multiply it by 1. These many moles of H2. Okay. Now let us pause for a little bit, right? This question is going on, it's a long question, right? I specifically has taken such a difficult question because taking easy questions is of no use for these examinations. You have to take difficult questions. This one difficult question is composed of almost 3 to 4 easy questions, right? So these many moles of water will be formed from 1 mole of strontium hydroxide hydrate, correct? But for us, in the equation, you can see that 1 mole of strontium hydrate contains X moles of H2O. So this whole part will be equals to what? This whole part will be equals to X. Yes, this whole part will be equals to X. So I just write this down here. Okay. Now, if you solve this equation, see, I'm not going to now move forward to solving this. Mathematics is not what I teach chemistry. So, solving this is your domain, solve it at home, but after solving, your answer will be approximately around 8. Or for me, when I had solved it, it came around 7.8, right? So this is a question where you can use your law of conservation of mass, mole concept and stoichiometry all at once together in giving you an answer. So now let's move forward into something much more easier, which is the next law. Next is law of definite or constant proportions. This is also one of the simple laws, right? See, to explain this law, let me take this example. We'll come to the statement of the law afterwards. Let me first throw some light on how this law works. You know H2O, right? Everybody knows H2O. So mass of hydrogen in H2O is, you have 2 hydrogen atoms, so 2 grams. Mass of oxygen is 16 grams. If you take the ratio, cut by 2, you will get 1:8. This is the ratio, right? Now, if I take this water from river, from my tap, or I take this water from the drainage also, or from the sweat that I am having right now, the formula of water will remain the same, right? Not only the formula, this law says that no matter from where you take this water, the ratio of the elements will be constant. So this ratio will be constant. That is what is meant by law of constant or definite proportions, right? Similarly, right, this is CO2, right? Here also you can see the ratio is around 3:8. So now, after you have understood the law, let us read the English statement which is written. It was proposed by Joseph Prost. Elements combine in simple ratio of their masses to form compounds. Yes, they do. You can see this simple ratio, right? Simple means which cannot be simplified further, and it is a simple whole number ratio. Remember, in most cases you will get a whole number ratio, right? The ratio remains constant irrespective of the source of preparation. So irrespective of the source, this ratio will remain the same. That is your law of definite proportion. Now this law also has a limitation. The limitation is this law is not applicable if the compound is formed from different isotopes of the element. What do I mean by that? You know, right? Isotopes have the same atomic number but different mass number. So if you have isotopes, you cannot use this law. This will become clearer as I move forward. So one of the numericals on law of constant proportions. So 3 grams of an element A. So you have an element A, 3 grams of it, combines with 8 grams of an element B. So it combines with B, 8 grams, to form a compound X. Some compound X is formed. In another experiment, see, this is your experiment 1. If I talk about, they have done some experiments, they are preparing compounds, right? So in one experiment, this is the case. In the second experiment, again the compound A is there, right? Yeah. Again you have A, which has 4.5 grams of A, combines with 12 grams of B to form a compound Y, right? So what your law said? Your law said elements combine in simple ratio of their masses to form compounds, and the ratio remains constant. Remember, the ratio remains constant irrespective of the source of preparation. So suppose this question comes in your exam, you do not know what they are talking about. Right now we have studied law of constant proportion, so that's why you know that you have to apply it. But if in examinations you will have a question isolated like this, how will you do it? Simply try and find a ratio here. The ratio here is 3:8. Let us see whether, this is the experiment number 2, whether you get the same ratio here also. So you have 4.5:12, right? So 4.5 is by 10:12 multiplied by 10, right? Right. Nines are 5. Okay. Then you have 3 and 8. So you have got the same ratio, correct? You have got the same ratio 3:8, which was here. Because the ratio remains same, because we are talking about law of constant proportions, means this ratio remains same. This is an example of law of constant proportion. So that is how you solve these questions. Right. Next question. Caffeine contains, yes, caffeine, the coffee which you drink, right? Every day, some people drink it in the morning, some people drink it to just ward off sleep. So the same caffeine contains weight percentage of nitrogen as 28.9%. Remember, what was weight percentage? Think about it. See, if I talk about weight percentage of nitrogen, that should be equals to mass of nitrogen in the compound divided by molar mass of the compound multiplied by 100. So if I talk about the percentage and substitute it here, this will come out to be mass of nitrogen is number of nitrogen, right? X may be the number, suppose, and one nitrogen weighs 14. So multiply it by 14 grams per mole, and the molar mass is given to you as 194, right? So 28.9 multiplied by 194 divided by 14, you have to get the value of X, right? And here, let me tell you a trick also. See, you can see this is 28.9, right? This is approximately equals to what? What is 28.9 approximately equals to? See, actually it is approximately equal to 29, but your answers, see, 3, 5, 4, 6, they are very far apart. So if you even take this as 30 instead of 28.9, you will still get this answer, which is 4. Yes, X equals to 4, which is the third option, right? Now moving forward to to the law of multiple proportions. Right? Law of multiple proportions. This is one of the laws which is little difficult to understand, but that is my job to make it simple for you, right? So, conditions for this law, I'll see the law, we'll come at the law at the end when you have already understood it. Then we'll come to the statement of this law, right? First, let us move towards the conditions for this law. The conditions for this law is that two elements should combine with each other. Yes, two elements should combine with each other first, right? We should not have aluminium and magnesium, right? These elements do not combine with each other. So we need some elements which combine with each other. When this is checked, those two elements should form two or more than two compounds. If there are two elements who form only one compound, this law does not work. We need those two elements to form, like element 1 and element 2 should form more than two compounds. Okay, so move forward. So like here I have taken the example of carbon and oxygen, right? So carbon and oxygen forms two types of oxides. One is carbon dioxide, other one is carbon monoxide, right? To apply this law, first step that you have to do is you have to fix the mass. You have to fix mass of one element. You have to fix the mass of one element. Like here it is already fixed. You can see the mass of carbon is fixed, correct? Here carbon is 12 grams. Here also carbon is 12 grams. Now after the mass of one element is fixed, now shift your focus to the other element, right? You can see O2 is here. O2 mass is 32 grams. Oxygen's mass here is 16. Now this is a fixed mass of one element. Now take the ratio of masses of the other elements. So you have 32 and 16. The ratio is 2:1. It is a simple whole number ratio, right? Simple whole number ratio, right? So this is the law of what? Multiple proportions, right? That I am not talking about these two elements in one compound. I am talking about these two elements in two different compounds, fixing the mass of one element and then taking the ratio of masses of the other element. And that comes out to be a simple whole number ratio. After you have understood this, now let me read you the statement, right? See, for these laws, if I directly tell you the statement, you will understand nothing. So, solving and examples are essential. So, let me go to that. Again, if you have two elements, right? 1 minute, huh? Two elements you have, check, I have two elements, carbon and oxygen. Chemically combined to give two or more compounds, check, yes. One carbon dioxide and one carbon monoxide, two compounds are there, check. Weight of one element combining with fixed weight of the other element, fixed weight of the other element, yes, carbon's weight is fixed, so that also is checked. Is in the simple ratio of whole numbers. So weight of one element combining with fixed mass of the other element, that one element is what? Here, that one element is oxygen, right? In this definition, the weight of one element combining with fixed weight of the other element, that one element is oxygen, and you have a ratio, and that ratio has to be simple whole number, right? In simple ratio of whole numbers, right? Easy, right? So that is what we will do at Knowledge Hub. We will simplify this complex statements which look complex but are actually simple. So let me take another example of two elements, nitrogen and oxygen. So first step, what you will do? You will fix the mass of one element. Now if you can see here, if I talk about this, Nitrogen has mass as 14. So if you have two nitrogens, here the mass is 28 is to oxygen's mass is 16. Here the mass is 14 is to 8. Wait, 16, sorry, it is 16. 16. Here again it is 28 is to 48. 48. Right. You can see here now in this example, the mass of one element is changing, right? That does not work for us. We have to fix mass of one element. How can I fix mass? See, this mass is the lowest, 14. What if I want to make this also 14 and this also 14? Simply divide complete ratio by 2. So if I divide it by 2, you will get NO half. This will be 14 is to 8. See, this I won't change. Let it be 14 is to 16. And this will be divided by 2. Again, let us write these things here. We use a different color also, so things will be similar. 14 is to 8. This is 14 is to 16, and this becomes 14 is to 24. So now we have two elements forming more than two compounds, that is, they are forming three compounds. Now I have fixed mass of one element. Then I move my concentration to the other element and take a ratio. So the ratio will be 8, 16, 24, right? Divide completely by 8. What you will get the ratio? 2 is to 3. Check whether this is a simple whole number ratio or not. This is a simple whole number ratio. Right, this is a simple whole number ratio, right? So this follows the law of multiple proportions, right? So today's class we will end with this law. Before I end this, let us have some examples and let us try and identify law of multiple proportions in various groups of compounds. See, you have carbon dioxide and hydrogen. So one of the ways to identify this law is that both elements of both the compound should be same. Here you can see that one element is carbon, other is oxygen, but in the one other compound you have hydrogen and oxygen. So you have not two but three elements. So the law of multiple proportion does not work here. Now here this example, you can see both of the elements are common in these three compounds. In these three compounds, both elements are common, right? So the law of multiple proportion is valid only in these elements. But as you move to the fourth compound, you have introduced another element which is hydrogen, and hydrogen is not present in these. So ammonia does not follow this law. Finally, going to the third example, you can see sodium common. So one element is common, checked. What about the other element? No. You have chlorine, bromine and iodine. These are different elements. So again, law of multiple proportions is not valid, right? That is how you identify law of multiple proportions, right? You should have two elements and those two elements should be same in all the compounds. Number of these elements can change, but the elements should be same. If they are not same, the law is not followed. These are some examples where you can see common elements are same elements, same. Here also HS same, carbon, oxygen same, sulfur, oxygen same. So these are some of the examples of law of multiple proportions. One limitation at the end of this law is that this law is not valid for isotopes of the same element. Isotopes, I think you know, they have what? Same, I told you already, same atomic number, different mass number, right? So you can see this is the atomic number which I have written at the bottom, and this is the mass number. Different mass number. This is hydrogen, this is deuterium, this is tritium, and with hydrogen we get H2O, with deuterium we get D2O, and with tritium we get T2O. So here also you will treat this hydrogen, this D and this T as different and separate, and here too law of multiple proportions is not valid. So isotopes do not follow this law, right? So there are some numericals also on this law of multiple proportions, right? So this is the last numerical which I am going to discuss today, and we are going to finish law of multiple proportions. In the next class, we will learn about some more laws, but before that, let us have a look at this last numerical. So 6 grams of A combines with 16 grams of B. So you have A combining with B. A and you have B. 6 grams combining with 16 grams of B. To form a compound X, yes, it forms a compound X. In another experiment, you have 3 grams of A combining with 4 grams of B to form a compound Y. So this data illustrates what? Which law does it illustrate? See, first find the ratio of these. So we are learning about multiple proportions. So we know that first we have to make this gram same. To make this gram same, divide both sides by 3 in this ratio. If you divide it by 3, you will get 3 is to, so B to find, okay. 1 minute, it should be, sorry, this should be, okay, I feel that there is something again wrong in this question. 3 is to 4. Let me check. 1 minute. Divide this by 2. I think 2 also will not work. 6. Okay, there is something error in this question. Let me check it out. In the next class, I'll take up this question again, right? Where I will be discussing about laws. Till then, stay tuned with Knowledge Hub, and as I say at the very end of every slide, at the end of 1 minute, a little miss happening. Yeah, let me just get the last slide. Yeah, so you have it. So we learned about various laws. Laws of multiple proportion is where we end it. Now, if you want to learn more about courses of Knowledge Hub by Sri Chaitanya, the code is here. Pick up your phones, scan this code and join us.